So, welcome everybody to another session of Lógicos in Quarentena. This, I have to say, this is a very special session because now we don't have only one speaker, but we have three. Marco Panza, Daniele Struppa, and Domenico Napoletani. I would like to thank you very much for you three who kindly accepted our invitation to give this talk. And there is also another kind of information because that should be occurring by now, the Brazilian Logic Conference, but due to the pandemic, it was postponed to the next year. So this talk is something like an honorary talk for the Brazilian Logic Conference. So when you are ready, you may begin. Thank you very much.
Yes, the problem is that Daniele now.
No. I'm good.
Okay. Can I see? Do you see the slides?
Yes, perfect.
Okay. So thank you very much for inviting us. This is a joint work, not only a joint talk, but also a joint work in a very, very precise sense of the term, that the three of us has different competences and familiarity with different aspects. So I think that nobody of us could have written alone the papers that we wrote and present alone the talk, because this is really an interdisciplinary effort that we made all together. I have no problem to confess that there are some parts of our paper that is very difficult for me to control. I needed an explanation by my colleague to understand what was the question. And I have also to say that I made a lot of effort to convince my colleagues of some philosophical views in the papers and also in the talk. I remember the first paper that we published after 5 or 6 years of discussion, because there were no way to agree on the notion of model. I remember that the discussion of the notion of model took, I don't know, 5 years of discussion between us. I think that you can confirm.
In Mexico, in Italy, in the United States.
Exactly, in any part of the world. Okay, so now leave this apart and let's go with the talk. So the idea is that we share the slides. I will begin to present some part of the talk. Then I will leave the other of us to present it. And we will try to speak around 45 minutes to leave time for the discussion. Or perhaps a word about the title. The basic idea is try to understand two things: the way in which agnostic science works, and I will tell something about what agnostic science is in our language, and overall also to try to understand the way in which mathematics enter agnostic science, that according to us is essentially a different way than the way in which mathematics enters classical science. Classical science, I want to say, the basic idea that we have is the Newtonian model. So it seemed to us that agnostic science is an example of a new sort of modality of mathematization. So the aim of our work is double. On one side, to understand what makes agnostic science work when it works, because of course it does not work anytime, and to try to understand what is the role in mathematics in this. Okay, I think that the first things to say is what is agnostic science. So the idea was to try to understand the way in which data analysis works, or how we say usually today, big data. Possibly the modality that we call agnostic science is not only proper to big data. I think that factually it is only proper to big data today, but it's not only proper to big data as such. We can imagine other sort of sciences in which the modality that we call agnostic science operate, even if to the best of our knowledge, today this is opening only in the case, it is the case only for big data. And essentially, the basic idea is that we forecast or we solve problem without understanding. So what does it mean without understanding? It means that it is not because of a previous identification of the internal structure of a possible internal structure of a phenomena. Of course, after Kant, the internal structure of phenomenon is not essentially the internal structure of the reality. The internal structure of the way in which a certain reality represented, phenomenally represented. So without having this previous understanding of this internal structure, we can still answer questions about possibly not the phenomenon itself, but some question concerning the phenomenon itself. And we insisted a lot in our first paper on the fact that in this case, we are not explaining the phenomenon. We cannot, exactly because we are not understanding, but we can answer some question concerning the phenomena. Now, what does it mean exactly without understanding? One of the problems that we had in the very beginning was the following. In order to make clear what we mean when we say without understanding, we should before understand what is understanding. And this was a big problem because there are on the market a lot of different conceptions of scientific understanding. And it's quite difficult to find the one that is the good one. And so we had a lot of discussion about that. And in the end of the story, we arrived at the conclusion that we don't need to understand what is understanding in order to understand what is without understanding. Because in some sense, there are some conditions we think that if they are not respected, certainly there is no understanding, independently, regardless of what understanding is. And one basic condition, we identified the two basic conditions without meeting with, we cannot have understanding, regardless of what understanding could be said in a more precise sense. One is the capacity of identifying among the variables that we consider relevant for the relevant problem, the principal one and the dependent one. So we say that there is no understanding if we are not able to say which data determine other data. We have a lot of data in front of us. We are not able to say that we can eliminate some of them because it's enough to give the value of some variable to have also the value of other variables. You know, that is the typical way in which Newtonian science work. Is enough to know speed, punctual speed and position of one body in order to have the trajectory of the body. So in Newtonian model, what is essential in this Newtonian model is that we are able to identify what are the independent variables and what are the dependent one. And we think that if we are not to do something similar, we cannot speak of understanding. Another aspect that we think is necessary condition for understanding is the capacity of change of scale. The capacity of change of scale in our quantitative description of the phenomenon is also, according to us, a necessary condition. So when we say without understanding, all what we want to mean is that these two necessary conditions are not met. Okay, then we can discuss about what is understanding, but this is another story we do not want to enter. So in the case of data science, what is agnostic science? Agnostic science is the practice that is done by a lot of scientists to answer questions about phenomena of which we are not understanding in its sense, but about which we have a lot of data available. So the question is enough to collect enough and sufficiently diverse data regarding a phenomenon in order to ask most relevant question concerning with it? This is, of course, the hope of data science. In some situation, this hope is realized, in other it is not. Our question is not to take a ideological position that consists in saying it should always be realized. So data science is a fantastic, so we are fan of data science. It's no more to say data science is horrible because we cannot simply base of data to make a solution. So we have to reject the data science because it does not conform with the usual pattern of science. We don't want to take no one of these positions. We know that in certain cases it works, in other cases does not work. As the basic question is when it works, why it works, how it works. And if we think that if we can answer this question, we can also answer the question why it does not work when it does not work. Okay, this is for agnostic science. Blind methods, we call blind methods the particular instances of agnostic science. That is essentially the method of application of some algorithm that are able to provide answers to the question that we want to answer without having a priori input given by the understanding. In particular, a priori input given by the identification of the principal variable and the procedure of changing a scale. And the last point that I have to say on these slides is what we call forcing. Forcing is a word that the philosopher of mathematics, and particular set theory, knows very well, but we don't want to use in this sense. So we tried sometimes to change the word to avoid confusion, but in the end of the story, we did not find a better word. It means that some mathematical technique, in particular some algorithm, are forced to phenomenon independently of the fact that we have a sufficient understanding of the phenomenon to be clear that is technical are exactly what are proper to this phenomenon. So in some sense, we select the method before to looking at the phenomena, and we force the phenomena to be submitted to this method. This is, when we will go into detail, I think that this would be clear. Do you want to add something on this first slide?
I don't think so, because otherwise we're never going to get to the end.
Okay, so the central principle of agnostic science. Data are processed to an appropriate algorithm that works on the available data independently both of their specific nature and of any knowledge concerning the relation possible connecting the relevant variable. This is essentially what I already said. So perhaps I have to come back here to say that one thing that I not is that, of course, the absence of understanding make that any phenomenon is to be considered independently of other. So the method are the same in some sense because they are forced to the phenomena, but they work on different phenomena in different way. So we have not a possibility of generalization. So of course, the process is subjected to normalization constraint imposed by the data rather than by the unknown structure of the phenomenon. To make an example, if we want to, in the end of the story, our idea is that data science is essentially a process of interpolation. But interpolation on which functional space? If we had understanding, we can consider that the functional space, that is the sort of function that we want to be the answer to the interpolation problem is decided by the characterization nature of the phenomena. Here, that's not this way, exactly because we have not understanding. And so the idea that we impose that the interpolation is by a certain sort of function, for example, a polynomial function, or much more generally a smooth function, or a function in a much restricted functional space that we will consider case by case. So this trait and produce an output which is taken as an answer to a specific question about the phenomena. In this, it's very important that I say which is taken to be, and not which is, because in absence of understanding of the phenomena, we have no real way to know whether the answer that we give is the right answer. We have to take a decision about that. The decision is governed by some criteria, of course, but is a decision. For example, we can say that we identify a minimum. We can see whether a minimum of the function is identified when it is a question of optimization, but we cannot know whether it is a local minimum or a global minimum. So simply we decide to set a certain minimum as the global minimum, give the good answer, and we have no other way to do it because we have no general understanding that allows us to identify all the minima, and to take the global one. So in this sentence, is taken to be is the essential point. We take to be an answer to be a good answer. Okay, I think that now, Domenico.
Yeah. Okay, so when we look at this whole setting, this whole framework that we are building, one thing that we need to stress is that we were motivated by the very sense of what are the methods that they are significant in practice. Now, this is not as easy as it appears because of the fact that in reality, there is a tremendous variety of methodologies that have been addressed, that have been developed, that are still being developed. And so these examples that we're giving, they actually try to converge onto particular instances that they are significant in terms of methodology. Supervised machine learning, which is a broad umbrella under which several methods will fall, including what now goes under the name of deep learning, is actually significant in that there is a structure that is superimposed onto the problem itself. This structure is an input and an output. And what is given, what is assumed that is given, is several instances of the problem in which the output, not only the input, but the output is known. For example, imagine that you want to understand whether the fundus, the back of the eye, has some pathologies. These pathologies could be pathologies in terms of glaucoma, in terms of macular degeneration, and what is available is only the image itself, a high-resolution image of the back of the eye. In a case like this, what supervised machine learning assumes is that for some instances, the image of the back of the eye is given, and is given the labeling of which disease is present for that particular image. Given this set, then essentially what one tries to find is a function that is able to the best, in the largest number of cases with the best accuracy, to match the input to the output. And you can see how this relates to the idea of maximization or minimization that Marco was talking about. This is important also because, as you can see, it's quite rigid. And maybe we will have the chance during the discussion to talk more about it. You need to set the problem in this particular format. Otherwise, it does not work. The second method, from the point of view of agnostic science, is even more significant. The second method, what is called boosting, essentially assumes that there are situations in which we may be able to carry some information about the problem, but very, very minimal information, maybe just better than flipping a coin. So going back to the problem of understanding diseases, pathologies in the eye, one may be able to roughly get a sense that, okay, this is not a normal eye. And maybe you are right 52% of the cases that you are presented to. This would be a very bad classification, a very bad system of diagnosis. But there is a methodology called boosting that we will talk about more later that actually is able to take an entire collection of such weak classificators that do not have knowledge and actually bring them together in such a way that the overall, what is called the ensemble classificator, becomes actually very accurate. So usually we're talking about a weak classificator that is just better than random, 51, 52% accuracy, that can reach all the way to 90, 95% accuracy. This, again, without any overt new knowledge given to the problem itself. All of these actually, that may seem that they are abstract methodologies, but in reality, actually, they are turning out even very, very recently, as you can see in December 2020, to give stunning results. DeepMind is a company, it's probably most of you may be familiar with this company. It's the most successful artificial intelligence company that is working right now. It works with one single methodology in mind, that essentially when you do learning, you may not have a clear sense of the whole problem, but you may have a sense of how an answer is better or worse than what you want. This is called reinforcement learning. You learn from your mistakes, or you learn from the fact that you are improving your performance as a machine. First applications were to games. Why? Because games have rules that they are relatively simple and clear, and so easier for machines to learn. AlphaGo, you may have heard again from the news about this algorithm that was a precursor of these algorithms, AlphaFold, that I will talk in a second. They are algorithms that, based just on machine learning, without any human supervision, they were able to beat the best, the champions of the game of Go. That is a game of strategy that is considered in several order of magnitudes more complex than chess. Recently, what they managed to do is with the very same techniques to actually learn from the base coding in RNA of proteins to actually get the three-dimensional structure with this algorithm called AlphaFold. This was the main problem in computational biology, essentially, to be able to go from the coding of a protein to the three-dimensional structure. And the accuracy now of a completely, remember, this is a completely data-driven algorithm, is actually comparable to the best structured computational methods, as well as the best knowledge that we have right now on how proteins actually are folding. So this has been a stunning development that, as you can see, is very recent. And I will stop here for this slide.
Daniele, please unmute your mic. Control D. No, it's in the Meet, at Google Meet. Just unmute your microphone there, please.
Okay, I think I'm good, but now I need to share.
Yes.
So now let me go and share the thing.
No. Okay.
No, I don't think you've seen my stuff. Oh, for Christ's sake.
We are seeing your screen, Daniele.
Are you seeing my screen?
Yes.
Ah, okay, great. Okay, you good?
Yes.
I have some sort of a feedback, so maybe, I don't know. Okay, go. So I wanted to make a comment before I talk a little bit about the slide, because Marco made some initial statements about how these, we wrote several papers on the topics. We have a fairly extensive bibliography by now. And he pointed out how, we brought together people with different expertise. My friend Domenico is more of a data science person, is a more applied mathematician. I'm more of a theoretical mathematician. Marco, of course, is a philosopher. And so we brought into different approaches. But one of the things that to me made this work interesting is also we have very different questions that we are asking or that we are interested in. As you heard from Marco, one of the key questions for him is, what does this new use of big data says about science, about math? I mean, what does it mean in a way from an epistemological point of view? How do you acquire knowledge? And this new way in which we acquire knowledge through data science is quite different from the Newtonian paradigm, for example. For me, as a mathematician, I guess that my real question is double. One is, why does data science work? I told this story in another setting, but one of the reasons why I got interested in this, because Domenico was my doctoral student. The best possible doctoral student you can imagine, because he had his own ideas and he was doing whatever was of interest to him. And I was sometimes frustrated because we were looking at some problems together, and while we were getting some interesting results, I didn't see, I couldn't justify to myself as a pure mathematician why the results were working. We did some work on denoising of signals or signal separation, or he was mentioning something about what you can do to look at the retina of a person to distinguish whether or not there is an incoming case of retinal problems. And while the results we had were very exciting and very good, you couldn't mathematically prove that you were right. So as a pure mathematician, I guess that was a frustration for me. And the positive aspect of the frustration was that I wanted to understand, why do these methods work? And will they work every single time, or is it something hidden that will tell us when they can work? And so this becomes, from my perspective, also a new way in which math can be useful. So the way I look at this, as I work with Domenico and Marco, is what can mathematics say about this question? What can mathematics say about the question of when will these methods work? When will blind methods work? And is there maybe something deep that we can say? And I think probably Domenico is going to touch upon it in one of his future slides. Can we find some deep reason why the methods work and an idea of which settings they will work? So that was really my approach. And I wanted to offer this because I want to make sure you understood that we really are looking, even though we are working together, I think sometimes our motivation are somewhat different. So Marco talked about agnostic science in the first couple of slides, and one of the words he used was this word of forcing. And the first comment I have here, that the first bullet is essentially a summary of what he said. We are using mathematical techniques that are not motivated by the phenomenon, but only because we know those techniques and we believe that they can allow us to structure the data in a way that will make it more amenable to further analysis. And there are several examples of these, one of which in particular we will be spending a little bit of time in the next few slides. But the first is the idea of smoothness. Reality is not smooth necessarily, and in fact there are some situations in which you only have discrete data, right? So you study populations, most of the data you have is discrete. And yet there is an entire area of work which is called functional data analysis, in which we, and I'm going to use quotation mark here, pretend the data to be smooth, so that we have a function. And why do we do that? Well, because we have calculus. So once your data are given by functions, you can employ tremendously powerful method to study those data. And yet you know that the data are not smooth. So this book that I quote here, Functional Data Analysis by Ramsey and Silverman, is a fantastic book. It contains a lot of examples of situations in which this approach, that if you think about it, that really doesn't have a very good motivation, actually works extremely well. And so this goes back to my question that I asked many years ago that has been driving my interest here, is how do we understand which problems can be dealt with when we force upon them something like smoothness? It cannot be that every problem will work that way. The question is to understand that, is there some kind of isomorphism, and we'll talk about that later with a different word, between the algorithms and the ideas we use and the phenomenon that we're trying to study. The second example, and I know that Domenico will say quite a few words about it later on, is the issue of optimization. a very large number of algorithms that are used to deal with complex, large set of data end up, sometimes unexpectedly, to be optimization algorithms. Domenico will probably highlight a couple of examples in which a priori you really don't expect the method to be an optimization method, but then when you actually analyze what's happening, you realize that you're optimizing a function. Well, again, this seems to me is almost a philosophical assumption. Why should be a minimum or a maximum of a function be the one that gives you the result? And as Marco pointed out before, in many cases, you don't even really know that that's the minimum. You use steepest descent methods, and we know very well that there is no real reason why you could expect to actually get the global minimum. You can be stuck on a local bowl, and that's where you are. So this is another example in which we sort of philosophically decided, the community decided optimization is a good way to go about solving problems. And so the question again for me as a mathematician is, can I a priori be able to understand which problems are amenable to the solutions and which are not? And when I understand which problems are, I need to understand the why. So that's really the issue. So forcing brings me back to the general question that I really want to understand, which is, why does data science work? And how can I use math to explain the remarkable success of data science in the absence so far of a solid, sound, theoretical understanding of why that is so.
Okay, now it's my turn to come back. And before I go ahead, I think that we need to make a clarification, to do a clarification. I present a clarification because this was one of things on which I insisted a lot in our collaboration. To understand the point, consider the example of PageRank. PageRank is an algorithm that is used by Google to assign weight to web pages, so to classify them and to choose them, to give a ranking to them. It's called PageRank because one of the authors is not only because it works on pages, but also because one of the authors is Page. And so this was invented in the 80s, if I remember well, and it's still at the basis of Google, even if Google uses other algorithms too. So this is a case in which we have the algorithm work. We can explain how it works, but I don't think that is very important. The important point is that we have no control on the way in which this algorithm classify pages. And why? Essentially because it is an iterative algorithm that assign a priori a certain weight to such page, assigns this weight in a very arbitrary way. By that, then by continuous, a very quick and a lot of number of iteration, arrive to a weight that is the good one, even if started from so we can start from any weight assigned a priori to the pages, and the continuous iteration make the page have the good weight. Now, we have no control on the way in which these are going to work. We cannot know why a certain page is ranked before another, really. But we know that the process converge. We know that the algorithm converge, and the algorithm has been constructed in order to identify a certain property of the pages that we call importance. The fact that it is really importance, that is not so essential. The point is that we have a proof that the algorithm converge to a rank that correspond to what we call importance, measured in terms of link internal, link external. So there is no absence of understanding here. There's absence of control, but not absence of understanding. So we need to make a clear distinction between absence of control of the algorithm, as in this case, simply because we have too much data The algorithm is managing to match data in a very, very short time. So there is no way for a human to enter there to understand what is locally do, but the human perfectly understands globally what the algorithm is doing. And so we have absence of control, but not absence of understanding. So it's important also to make clear that what we are speaking about here is agnostic science. That is absence of understanding, not simply absence of control. There are two distinct things, and the case of PageRank make clear how and why they differ. Okay.
Yeah, so I'm going to go back quickly to the, I say quickly because we are kind of moving forward with our time on the issue of optimization. The idea that optimizing, finding the minimum of a function is the way to solve a problem is obviously an idea that goes back to several hundred years at least, and we pointed it out in one of our paper. But this is really, I would say, a very good example of how mathematicians force a technique that they control over a large set of data. So what do we mean by optimization? Well, the idea is that you build a function, usually we call it fitness function, and this is a function of the data that are available, and you want to find when this function has a minimum. Now, this is very helpful, in particular, when you're dealing with a very large number of parameters. And when I say very large number, as the slide here indicates, we're talking about millions of parameters. So something that could not be handled in many other way. And in many cases, actually, one used very simple technique for doing optimization, which is the gradient descent method. So essentially, you move in the direction in which there is the strongest slope, and you expect that this will bring you to the minimum. And clearly, if any one of you has ever been going hiking, you know that this method doesn't necessarily take you to the bottom of the mountain, but it will take you maybe to a valley whose minimum is way above the bottom of the valley that you really want to reach. And as Marco pointed out in his discussion of the third slide, we then claim this minimum to be the solution of the problem. Marco was quite emphatic in saying that we obtain a result and we assume, we take that to be the solution, even though that is not necessarily the case. Now, what is fascinating, as I said before, is the fact that this optimization really appears in a huge number of settings, even when it's not obvious. In the next slide, Domenico is going to talk about a very powerful methodology that is used in data science, which is called boosting. And as you will see from his description of boosting, it is not apparent in any way that there is, in fact, once again, an optimization technique. So here I've made a list of a class of method which data sciences uses optimization. But what I think is important to know that in some cases, this is very explicit, and there is a construction of a function, and people are looking for a stationary point of that function. But in some cases, like in boosting, this is not a priori obvious at all. And in fact, the method is built almost thinking about a different approach. But then it turns out that when you write mathematically what's going on, what you're really doing is optimization. So I think Domenico is now going to go into the boosting description.
Okay, so coming back to boosting that I was already briefly presenting on, I told you the basic idea of how it works, which is the most important point to consider. We can start with extremely weak knowledge, but keep in mind, there is a very slight knowledge because it's not the same as flipping a coin. You are able to classify the images. For the case that we were using as a sort of, for continuity, we are using always the same example of the back of the eye and the presence of the absence of disease. And you can get to classifiers that they are very accurate. How does this work? Let me say just a few words because it's very enlightening to understand how this works. Imagine that the presence of disease is associated, if there is disease, to a +1, if there is no disease, to a -1. You start with your data. Imagine that you have 100 instances of images, and you know whether there is or there is no disease for that particular image of the back of the eye. You're going to be right for 52 out of 100. You take the classifier that is able to keep this particular result, and you set it aside. And then for all the instances, all the images where you did not get the right result, you increase their significance. So you decrease the significance of the images where you have been already right, and you increase it where you have not been right. Now you have this new sort of modified set. It's the same set, but it's kind of weighted differently. And again, you try to classify. You get a new classifier that will be right on some other subset of your 100 images. Whatever it is, you repeat this process, and you set the new classifier apart. So you're creating sort of a history of classifiers, one after the other. And then simply what the algorithm does, it takes all these classifiers and it weights them together to get a number. If this number is positive, then the algorithm will say, yes, there is disease. If this number is negative, it will say that there is no disease. So as you can see, there are two elements here at play. A reweighting of the data without really knowing why each instance of the weak classifier was not working. But we know that it's not working. We change slightly the data. And then this idea that we can learn by keeping the history, the entire history of how this process is done. One thing that I want to say that is going to be significant later in the talk, if we reach that point, is the fact that this sense of moving somewhere should not really end up in some static situation, because if it does, then what it means is that we're done, which would be good, except that we could also be somewhere where our ability to solve has become static, where we are not able to improve anymore. And so this really leads us to try to understand this method is completely blind. Boosting methods, they work in a way that is very opaque, very hard to understand how this significant knowledge can come from very, very minimal knowledge. It's not the same as making just voting, because there are very fine-tuned weighting that they are involved in this process, and the dynamics of what is happening is very complex. But at the same time, our attempt has been through the years to substitute an understanding of specific phenomena in an understanding of, and this is our conjecture that has been leading our thinking for a while now, that there is, while there is no correspondence between a model and a phenomenon, there is a correspondence between the structure of the algorithms and the phenomena that are better suited to these algorithms. And so essentially, if this is true, then it's the structure of the blind methods which determines which problems are most suitable for this framework. And so then when you bring it down to the very core, when you try to look at the overlapping of all these methods, what do these methods have in common? We end up to something that looks extremely simple, and is what I was mentioning for boosting algorithms. Essentially, when you have a black box, whereby black box means that you take an input, you feed it to a machine, you get an output. What is it that you want? You want either that the output, as you continue to sort of improve your algorithm, to give more data to the algorithm, is stabilizing. And so theoretically, this means that one has solved the problem. Or if we are in a situation in which our method has become incapable of improving itself, we need to replace it. Super simple. I mean, this is something that is almost trivial in its outlook, but actually has been used in multi-scale methods in such ways that they actually have been in such way that they've been actually suitable for the solution of, for example, fluid dynamics problems. They've been solved exactly with this very simple approach in mind. And now one of our contributions has been to realize that this principle, in its simplicity, is actually applying to optimization in general, but also in general to the dynamics of data science algorithms. And so our claim is that most optimization methods, but also by by the fact that optimization methods are so significant for data analysis and data science, also for all data-driven algorithms, this principle is in some way the guiding basis of all of them. How do we go about using it? Essentially, what brand principle is assuming is that the validity of solutions is verified not along the way, in line, while things are being solved, but actually only later, when one looks at these solutions and has a rough understanding of whether they are suitable, not optimal in any way, but they're suitable for the problem at hand. And optimization, when we look at this point-by-point optimization in which one tries to find the minimum, just by looking nearby, as Daniele was saying, by looking at the gradient, by looking at where one is going just nearby, then again, if we reach a minimum, what happens? You have nowhere else to go. And so the algorithm has found a solution or has ended up in a place where it cannot improve itself anymore. The question then becomes, where can we use this principle? So do we have actually sets of solutions, sets of problems where this method is particularly, this brand principle is particularly suitable for application? And so we need to understand what we can learn by these general considerations, that each one of them, this I think is something also that I want you to note, that each one of them, they're simple observations on how data analysis is actually working. We're looking at the methodology, but we're looking at what they have in common and what is simple about them. But what is interesting is that when you put them all together, the conclusions are not necessarily simple. And this is the main point that now we're reaching here, that agnostic science is telling us that if we have a large enough set of variables, then we can predict other variables. Mind you, this is not necessarily the case that is true, but it's an assumption that one is making when we get in agnostic science. Boosting methods are saying something different. And by the way, a more general term, this is the most significant, boosting methods are the most significant of a class of methods called ensemble methods. What does it mean to have an ensemble method? That you take distinct classifiers, distinct solutions, and you learn how to bring them together. But of course, who would want, if you have to decide whether you have a disease or not, who would want one algorithm that tells you, oh, maybe yes, and another that tells you maybe no? Naturally, we try to blend distinct methods to get a better solution. But again, it's not necessarily the case that we will be able to get to one final classifier that is better than all those that are sort of making it up. But we seek that. And so boosting methods, ideally, they're seeking a unique classifier that is by blending together several classifiers. I want to mention that most methodologies that are used, for example, for Netflix to try to predict what movies a user would like to see, there are competitions that are done periodically. They're based on ensemble methods, meaning that different methods are put together and people can see that the solution actually does end up being better. But when you put together these two simple observations, then you end up with a form of analyticity. What do we mean by this? That the classifier function in the limit has to be fully determined by an infinite set of sample points. Again, we're never in practice with such an infinite set. But the conclusion of the way we use data analysis is that we expect such rigidity to the type of classifiers that we are looking for. And so I let Daniele or Marco continue on this.
Thank you, Domenico. So I mentioned before that as a mathematician, one of my interests is to see whether mathematics can help us understand when these methods are fruitful. But also the second interest I have is to see, can we use some of these ideas to sort of develop a different kind of mathematical approach to problems? So the example you have in front of you here is maybe one of the first examples in which Domenico and I look at a problem as kind of improbable as the problem looks like, and we try to think of a way by which this kind of thinking can attempt to offer a solution. So the problem came around just because Domenico and I were working on something else, and we were starting to read the work of Minnelli, who is a very well-known Italian biologist. And in one of his books, Minnelli studies centipedes. And he studies centipedes really from all around the world. And so the variation among the different species of centipedes is just gigantic. And some of them has a certain number of legs, a pair of legs, of course. And it turns out that there are only some possible numbers of pairs of legs that centipedes have. Now, this is kind of a curious thing, right? Because then the legs emerge in the process, in the process of the development of the embryo. At some point, the differentiation takes place and individuals develop appendices, or in this particular case, legs. So the question is, how come that all around the world, there are no centipedes who have 17 or 19 pair of legs, for example? Now, this obviously is not exactly a very applied question, but it's a curious thing. And so we work with another fairly famous biologist, Chip Petricoin, and we thought, how would we try to solve this problem? I'm not saying that we are solving it, but is there a way that we can frame this into a mathematically rigorous way? And so we wrote an article back in 2013, and the idea was the following. The idea is very connected to what you just heard from Domenico just a minute ago. So let's say that we have a very large number of biological variables, okay? So these are variables that a priori we may influence the number of legs that the embryo will eventually develop. And let's call Y the number of pair of legs that are associated. So now you have the space to the domain of a function that you're looking for is the variables in domain are the biological variable for centipedes across all the species that we have. So this is a very large database that we have. And the values of this function, Y, that we find in nature, are the number of legs that actual species have. So the question is the following: is it possible to show that if we are looking for a function f, the function that associates to the variables x, the biological variable, the number of legs, is it possible to show that every function of this sort, there is sample analytic, exactly for the reason that Domenico was mentioning before, is such that Y can never get a value, for example, an even values or a value such as 17 or 19. If we were able to prove that, that would allow us to explain, to have a mathematical explanation of what is the possible number of legs that centipedes have. Now, I'm not offering this example as an example of something that people should necessarily be spending their life on, but as a way to take a problem that is apparently untreatable, apparently mysterious. How can you even, we cannot know which particular biological variable will be determining the number of legs. And there are so many of those. And yet, with this approach, we can at least have a methodology in place, or a scheme, or an approach that could lead us to solve this particular problem. So the reason why I'm very fond of this example, again, is not because we ever hope to be able to find out how many legs the centipedes have, but because it shows that the reflections, the epistemological reflection we have made on data science, and in particular on big data, not only have allowed us to discover some fundamental philosophical consideration, but also can give us a pathway to a different kind of mathematics to deal with problems that a priori seems to be quite unsolvable. So I think we touched upon most of the major issues that we wanted to discuss with you. We have one more slide that Marco is going to discuss, which is essentially a set of conclusions that I hope we will be then discussing with you, and then an additional short slide with just a few of the references that we made reference to in this, and that the reference don't include the one here on segmentation.
Okay, no, it's not here. Okay, so some conclusion. Let's conclude, insist on the basic idea. first basic idea. Mathematics work here as a reservoir of ideas to force on phenomena, not as a way to structure phenomena, but as a way of a reservoir of algorithm that can, in some sense, make what humans do when identify the structure of phenomena, that is, identify invariants. This is what essentially the algorithm do, and they do it not because really of the fact that they are adapted to the structure of the phenomena that we don't know, but because there is a sort of analogy, a correspondence between the structure of the phenomena that we don't know and the structure of the algorithm. So the basic idea is that instead of trying to understand why the agnostic science work on looking at the correspondence of a method with the phenomena, we try to understand whether there is a structural correspondence between the way in which different algorithms succeed one to the other and the structure of the phenomena. And the idea is that agnostic science works when this correspondence exists. And more locally, they work if there is the phenomena, that there is what we call asymptotic analyticity. That is, in some sense, this correspondence of structure allows to identify at the limit a unique function that is the interpolation, the interpolation one. So, in some sense, mathematics is not here as a tool to understand the phenomena, but it is a tool to understand the way in which science without understanding work. So the request of understanding is displaced from the phenomena to the process of solution and answer to the question that the phenomena present to us. This is basically the essential idea that we try to identify. Science without understanding is not really without understanding. It's simply without understanding of the phenomenon, but not without understanding of the interaction between the phenomena and the algorithm. And this interaction can be studied in mathematical way by this idea of asymptotic analyticity. I think that I can stop here.
Show maybe the slide with a few references.
Okay, yes. These are some work that we are reading together on this. There are others, but these possibly are the more significant one. Okay, I stop here.
So, thank you very much for the really nice talk. So, as usual, now we have some time for comments, questions, any kind of interaction with the audience. Just to avoid a lot of people talking at the same time, I'd like to ask you to click on the raise hand button before talking. Well, as my background for computer science, I just would like to make also a question, because Domenico, when you were talking about boosting and reducing the complexity, the idea of making it better than a random number generation, were you talking about the kappa index?
What do you mean by kappa index in this case?
Kappa index is a metric that compares a classifier, how better it is from a random number generator.
Well, that's you're touching actually on an important point. Can you mute it? Because the implicit assumption of the whole theory of boosting is that indeed you can prove on a specific set of data that such statistical improvement with respect to random is there, which is not necessarily the case. But usually within the way the theory, and this is where it sort of diverges with the statistical analysis, it's true that only under such conditions the theory will work. But then in practice, the way people use, they never check this condition. And actually for most sets, there is probably no real sense for which this should be the case, that there is a better than random. It's a very general assumption that probably is not verified at all. One thing that I want to say also with respect to this that I think is significant with respect to the overall methodological approach is that this type of methods, that they're based on this statistical but very, very minimal assumption, actually they work best when the data are heterogeneous, when you're looking at data that they come from all over the place. So really, when you have no structure, when you are in the situation where data really are not structured, consistently, in practice, these are the methods, variations on the boosting methods are the best. But if instead you do have some pre-existing information, like the example I was giving of images, then it's not the case. Then methods that sort of learn much slower, like deep learning, like neural networks, then they work much better because there are assumptions that you can sort of build up yourself on. So there is a connection between how heterogeneous the data are and when these methods that they start with this basic assumption, they actually work.
Thank you. Well, also, while no one manifests first, a more general question. Well, because we have some kind of classical classifier that is the decision tree. A decision tree, I think, I believe that is something that you can understand why the outputs that one, because it says, oh, because this value is better than this one is greater or less. So when you have the forest considering a lot of trees, you cannot just merge it. So that is something that I think that is really interesting, because you have a lot of classifiers. If you take all of them lonely, you can maybe it's not agnostic because you know why they have that answer. But if you take all of them together, it's not simple to merge. Maybe you have some kind of democratic aspect because say what most of them say will take us through. I don't know how
I think you're absolutely right. I mean, to start with, decision trees are exactly the methodology that they use the most in boosting. And indeed, one by one, it's easy to understand. It's easy to understand also why they don't work well. But when you actually take them all together and you have a random forest or you have incredibly deep trees, that individual information comes together in ways that suddenly don't make any more sense. So it's almost by default that by putting together this type of methods, if you really try, you end up with something that does not have meaning, even though people nowadays are trying to talk of explanatory machine learning. But in general, for this kind of methodologies, the chance that they will work seems to be very slim, exactly because of what Bruno is saying. Really, that you cannot, even for us, even if you have 3 or 4, it becomes hard to know what is the meaning of bringing them together. We know what is the meaning of solving, but not the meaning of actually what they are, how they come together to make knowledge.
Yeah, sure. There is a possible connection. Maybe I'm not sure if it would really work, because you may take all of these trees, use some kind of tree automata that recognize this language of trees, and you have an association of these tree automatas to monadic second order logic. And not for monadic, but if you take full second order logic, you may associate it to set theory, and maybe you can try to look at it some kind of set theoretic expression, let's say it. But I really don't know if it should work. So, well, is any other question or comments from the audience? Gisele?
Yes, thank you. Thank you for the 3 of you. Very interesting. I unfortunately I didn't read your papers yet, But maybe some conceptual clarifications I would like to ask, maybe for Marco then. Hi, Marco.
Yeah, go.
So the very first conclusion that you presented, you said that mathematics was a sort of repository of ideas to be forced on, but then you used the word algorithm. So one of the things that I kept thinking when you were presenting is, so these basic notions, it's not clear to me how they interact. For example, is mathematics, in your understanding, just a bunch of algorithms, or just in the case of these specific applications? And the other one is about the very notion of blindness that is in play here, because it's for me, it is inevitable to think about Leibniz's idea of symbolic knowledge as blind knowledge, which also has to do with finding structures that are shared from the mathematical or logical systems, formal systems, with reality. So then so my first question will be about the relation between mathematics and algorithms. How do you understand mathematics as this repository in general, or just in this particular application of mathematics? And the second one is, if you could say a little bit more about this notion of agnostic science as a sort of blind knowledge, if it has something to do with this Leibnizian heritage or something.
Can I take the first one?
Yes, the first one is for Daniele and the second for me.
Yeah, so on the first one, no, I think the math is much more, the way we intend it is not just as a collection of algorithms, but really some of fundamental mathematical ideas, like smoothness, for example. So the idea is that we assume, in fact, we do some kind of a double force in there. One which is structural and the other is algorithmic. So we take data which are not discrete and we assume they to be discrete, to be continuous. So that is an imposition that we make on the structure of the data that we know not to be correct. And then, of course, we do a second form of forcing, because now we have this function that describe the data. Now we take derivatives or integrals. We do whatever we want to use with our calculus. So I think that it's not just about algorithms, but really is about these fundamental ideas. Another idea that is really underneath most of these, and Marco and Domenico hinted at it, is the idea of interpolation. That is not necessarily an algorithmic idea, but it's the idea that you can, given a certain functional space and certain pairs x, f of x, you can find actually, or I should say xj, yj, then you can find a function such that f of xj is always equal to yj, and the function satisfies some general mathematical properties. So I think that, though I can't speak for Marco, but I believe that when we say the mathematics is a reservoir of ideas to force, we are really not restricting ourselves to algorithms, but really the general principle of it. Even the idea itself, that we mentioned it several times, of Marco said it and Domenico said it, in the appropriate functional space. Well, that is a mathematical idea itself. It's not an algorithm, but the idea that functional spaces exist. What is a functional space? So those are very general ideas that I think have a significant impact on how we do this.
Yes.
Okay, but then I'm sorry. But then in this case, I don't see very much the difference between the usual way that mathematics is applied or used in science and this particular case of a data science or agnostic science.
Well, I think the way I would address that is that, especially through the process of forcing, these ideas are really not necessarily justified for the use in the specific phenomenon. So if I'm asking you what is the fastest way to go from A to B, and what is the curve that will allow the ball to go faster, well, that is a minimization problem. It's obvious, and in a way, there is a justification, because the question is find the minimum of a function describe this. But when we are trying to find, like in the example of boosting, trying to find the predictor, the idea that we might want to apply a minimization technique is an example of how you believe in the power of the idea, regardless of the fact that that the problem per se is not a minimization problem.
And if I may add something on this, there is also another aspect that is significant for the first example that Daniele was giving on functional data analysis, in which essentially it's discrete data sets where we know that there is no underlying continuous variable. But then the way functional data analysis works is that he assumes that we can interpolate totally discrete data, categorical data, to create a continuous function just because we know the differential equations are nice. So, and it works. It's been used in several cases where this sort of methodology has been working. So that's the kind of forcing is really that sense that we know that there is no continuity there, but we also know that continuity and differentiability are extremely powerful categories, and so we try to apply them.
Yeah, no, I like actually that Domenico made this point, because obviously one could say you're always forcing continuity, right? Let's say you take data of the movement of a body. You have discrete data, and so you say, oh, Daniele, you're assuming continuity. Yes, but the reality is that our understanding is that there is a movement that is a function that is not a discrete function. So the assumption that we're going to use this with a functional approach is not so surprising. But in the case that Domenico mentioned, we are talking about data for which we know that there is no continuity, and yet we pretend to use it. And I think Marco.
Okay. Yes. So to answer your question, I would like to let's take a very simple example, very, very elementary. I do not pretend that any application of data science works this way, but I think that the example is very identify the question. Suppose that we wanted to recognize a face. We have to identify a process of face recognition. And how did it work, the system? We have a certain example. We have a certain data on given faces, and we know to who the faces belong. So, in some sense, we give to the algorithm information that is based on a previous solution of the problem. Okay, so we gave a different photo of Daniele, and we say Daniele. We give a different photo of Marco, we say Marco. We gave different photo of Domenico, and we say Domenico. So in fact, we train the algorithm to identify a connection between two sorts of sets, the set of data and the set of person that we have to associate. So the algorithm identifies a certain function that is the function that has already solved the problem. Of course, this function is not really a function because there is a large family of functions that can do that. And so this is the reason which we speak of interpolation. The problem has been solved in the past, and so we have some value of y that is associated to some value of x. The x are the trait of the photo, if you want, of the visagers, and the y is the person associated to them. And then we choose between this infinite possibility of function, a certain function that associate the data with the x with the good y. And then here we solve nothing because the problem is already solved in the past. Then we come back on the past, but now on another past. That is, we make the recognize faces that we have already recognized, but we don't say to the algorithm that we have recognized. And we see whether the previous choice of function really correspond to the good solution to the problem that we have already solved, but we ask the algorithm to solve. And in this process, the first case is the training, we call the training set. In the second phase, we have, in the second moment, we have a sort of correction of the function resulted by the training set. Now we have no more, we don't give to the algorithm two set of data, the X and the Y. We give only the X, and we suggest to find the Y, and we compare the Y that is found on the Y that we know, because this happened in the past. And when we have in this way a function that appears to be good, in the sense that gives the good answer to past case of association between the face and the person, then we make it work on the future of something that we don't know, and we ask it to recognize new person that we don't know to recognize. So what is happening here? We don't know at all why what is the function that the algorithm recognizes. We don't know what data of the photo or my visage are relevant for making, because there are a lot of pics in the picture. So we do not really know how the algorithm is making the association, but we know that it made a good association in the past, and we hope that it will make a good association in the future. So in some sense, the algorithm identified some invariant, but we don't know which invariant. Some of the data that we have are more important than the other, but we don't know what of these data, which of these data are more important than the other. So in some sense, there is a process of auto-identification of the relevant invariant, and we don't know what they are. We simply know that this function worked well on the training set, this function worked well on the control set, and so we hope that it will work also well in the future, even if we don't know why it worked well in the training set and in the control set. And this is essentially, in a very, very simple case, how things work. So there is a sort of induction, but it's sort of the induction of data that we are not able to select, that have been selected by the algorithm itself. Plato said that knowledge begins by astonishment. And the astonishment is generally in Plato interpretation astonished by men that identify a certain dishomogeneity in something that is homogeneous. So we see things go this way and back this way. So this astonishment is driven by the invariant that is not, that pop up from the background. Here things go exactly in the same way, except that the pop-up, the astonishment, is not by the man, but the algorithm. The algorithm identifies some invariant, and it begins a certain process of knowledge because of the identification of them, without a capacity of knowing why what are these invariants that are relevant. Okay?
Any other question or comment? Okay, so thank you very much for the three speakers. It was a really nice experience.
How are you? You are good?